Welcome to this lecture series in number theory. In this lecture, we will discuss a certain primality test, and all we need to know is the definition of a prime and of a composite number, and let me not recall them. Some problems for practice, and now let us get started. So let me start with a question, just a computational question. Is 97 a prime number? Well, you may already know that it is, but if you didn't, what would you do? You would start checking, you'll start running through the list of all the primes which are less than 97 and see if one of them divides it. If none of them divide it, then you will declare that the number 97 is a prime. A little bit of thought will show us that we do not need to go beyond the number 48, or rather, let me say 49. Because 49 is bigger than half of 97, and any divisor of 97 cannot be bigger than half of 97. So you will be running through all the primes less than 97 and check for divisibility by each of them. And if none of them divide 97, you'll declare that 97 is a prime. Clearly, this is a costly process. So we'll learn a very small, very little, very nice fact which will solve or save a lot of computation. So this is called the Sieve of this ancient Greek gentleman whose name I don't know how to pronounce. So I'll just call it the Sieve. So fix a composite number. The theorem will prove a small lemma. So fix a composite number n. Then there is a prime divisor of that number which is at most the square root of it. So every composite number admits a prime divisor which is not too big. And the reason is very simple. Since n is composite, we can write n as a times b, where both of them are in this range. Right? Immediately by the definition of composite numbers. Okay. And now let me just say it. If both a and b were strictly greater than root n, then their product would be strictly greater than n. But since the product is equal to n, that would be a contradiction. So not both of them can be strictly greater than root n. Therefore, at least one of them is at most root n. And just pick a prime divisor of that guy. Let's say a is at most root n. Pick a prime divisor of a. It will naturally be a prime divisor of n, because anything that divides a also divides n, and it will certainly satisfy this bound. Since a itself is at most root n, every prime divisor of a will also be at most root n. So that's it. That's the proof of this fact, and this helps us check for primality. Suppose I'm given a number n and I don't know if it is composite or prime. I want to know whether it's prime or not, so I will calculate square root n approximately. Let's say square root n is some smaller than 17 maybe. Then I will only check for all the primes up to 17 and see if n is divisible by any one of them. If n is not divisible by any of them, then n cannot be composite because of this little fact. So, coming back to our original question, we want to check if 97 is a prime. We calculate the square root or estimate the square root, and one estimate is this. Now we need to check for division or divisibility of 97 by only the primes which are at most 10. And all those primes are listed here. And we can check by hand that 97 is not divisible by any of them. 97 is odd, so this is gone. 9 plus 7 is 16, so this is gone. 5 certainly doesn't divide 97. And this is just a simple check that, So none of these numbers divide 97, therefore this is indeed a prime. So this was much faster than going through all the primes up to 49 or something. Right? And that's it. That's all that I want to discuss here. This was a particularly simple lecture. And with that, I want to end it. As usual, like, comment, share, subscribe, and I will see you next time.